So with this J tube that you see, it's a little different than what you see in figure 4 on page 363, with the fact that this is open to the atmosphere. And what we see here, you have any type of gas, whether it's oxygen, hydrogen, helium, any one of those, because in that figure it shows this will opening with oxygen gas molecules exert a force or a pressure in this millimeters or in this mercury that, just like in a thermometer, it'll slide up, it'll slide down according to that of the temperature. So if we see something like this, okay, we're actually going to measure the difference between these two heights here, because this is all mercury inside this J tube, just like what you would see in that on page 363. So that gray material, it says pressure of oxygen gas in millimeters of mercury that's being exerted on here. So for problem solving, that's why we go through these, is if we needed to measure the atmospheric pressure with this, you would have to make a correction because it's open to the atmosphere. Now that doesn't mean anything to you right now, but we're going to go ahead and go through and show you how to do that. Okay, so a problem might state something like this. In an open manometer, the mercury is, we're going to say, this difference between these two markings of this mercury is about, I don't know, we'll say 77. Okay, the mercury is 77 millimeters higher in the atmospheric arm. Okay, the atmospheric pressure is, we're going to say 98 kilopascals. So what is the new pressure? Okay, so what that means is, here we've got two different measurements. We have kilopascals and we've got millimeters of mercury, but they have to be in the same label or same unit. So what we have to do is convert this millimeters of mercury into kilopascals, because since this is open to the atmosphere, as barometric pressure changes, okay, if the pressure is going down, when there's going to be less pressure pushing down on this, so this is going to be moving up. Okay, if the atmospheric pressure increases, there's going to be more pushing down on this, therefore moving the mercury further into this side. So what we see here, the higher in the atmospheric arm is important information right here. And this is why. Okay? When we separate these two, just picture a dotted line here, that on the left-hand side is the gas sample arm. And on the right-hand side, we see the atmospheric arm. And the reason we say that is this is open to the atmosphere. We see it's an open manometer. And that's what it's telling you right here. Okay? So the next thing we need to do is convert this to kilopascals. Okay? And in order to do that, we have to account for this correction here. So using dimensional analysis, just like what we've been doing pretty much all along since August, we're changing grams to moles, the same type of concept. You're canceling out your factors. So what this means is, if we have 77 millimeters of mercury, okay, we need to get that to kilopascals. Okay? So what we see here, one way we can do that is moving like in this direction. How many millimeters of mercury equals an atmosphere? Well, this tells you that we just read on page 364, it's 760. So, to cancel out millimeters of mercury in our next step, would we put that on the top or the bottom? We put it on the bottom. That's right. So, for every 760 millimeters of mercury, we get 1 atmosphere pressure. Okay? How do we know that? Well, it's one of the things that we had read on page 364. Okay? And it also tells you that on table 1, where we see where it says atmosphere ATM. It's equal to 760 and 101.325. Okay? So now that we got this in atmospheres, these have canceled. How do we convert an atmosphere into a kilopascal, do you think? How do we cancel out atmospheres in the next step? Put it on the bottom, because for every atmosphere, how many kilopascals do we get? What does it tell you up here? 101.325 kilopascals. Our atmospheres have canceled. Our millimeters of mercury have canceled. So now we're in kilopascals, and that's what we wanted. Okay? So, how do we solve for that now? What do we do when numbers are next to one another? You multiply. So 77 times 101, and then divide that by 760. Okay, 77 times 101.325 divided by 760, and we get 10.27. Okay, so this is 10.27 kPa. Okay? Now, back to this on why that's so important. Here's the reason why. Because this is open, we need to account for that correction factor of being exposed to the atmosphere. So, if the mercury is higher in this side, hopefully there's these little not a pseudonym, not an antonym. Little mnemonic device. Has anyone ever heard of that before? Okay. What do you think? What does a mnemonic device do for you? Maybe it's hard to explain. Gives you a very easy way to remember things. Well, we hope. Okay. For instance, for those of you who take anatomy and physiology next year, which, just out of curiosity, who would that be? 3. Okay? So, one of the things, what are 4 compounds in our diet that we have to break down to digest? What do you think? In anyone's diet? Just guess. Proteins, carbohydrates, like butter, fats, and oils, and the final one is nucleic acids, okay? But what we see is, what would be an example of breaking down something with protein in it? Did we have anything in today's lunch? If you ate the school's lunch, is there anything that you had consumed that would have protein in it? The eggs, and what else maybe? The sausages, because those are meat products, hopefully not meat byproducts. Maybe that's what you're thinking. But to break down proteins, there's not always one fix-all enzyme that does that. So inside your stomach, you have 2 types of cells. One of them is called chief cells, the other one is called parietal cells. They each secrete different substances. Okay? The chief cells secrete what we call pepsinogen. The parietal cells secrete hydrochloric acid or acid. So a way to keep that separate, a mnemonic device, would be what has the letter A in it, chief or parietal? Parietal does. So what we mean by that, since the parietal name has the letter A in it, it secretes acid rather than pepsinogen. That's a mnemonic device. Sorry, that was probably a long story that made me think, what are we getting at here? But that's how you can keep them two separate. So in this case, in this correction factor, you either have to add that 10.27 or you have to subtract it. But this is where, keeping these separate, which sample arm they're in, if it's higher on the atmospheric arm, this means you always add. Okay? So that way you hopefully won't ever make that mistake. If it's higher in the atmospheric arm, the AA stands for that, but also could stand for always add. Because if it's higher in the gas sample arm, what do you suppose you would do with that 10.27? You would subtract that. So hopefully that's a way that you can keep that separate. Okay? So the final thing is 98 plus 10.27. They're both measured in kilopascals. So our answer is what? 108.27. Okay? 108.27 kPa. So that's what the atmospheric pressure would be in this problem. The answer would be 108. You have to see which arm has a higher level of mercury in it, either the gas sample arm or the atmospheric arm. Make your correction from millimeters of mercury to kilopascals, then either add or subtract. Now, I'm not going to ask if we've had any understanding with that because we've only seen that once. But what about the converting part? Does this make sense to you? This isn't the first time you've seen something like that canceling factors out, correct? Because we've been doing that, like, would you agree, since last August, changing atoms to moles or atoms to grams, okay? Can I erase this? Okay. So now we've done something that was really, really difficult. Now maybe let's do something a little easier. All right. Perhaps convert. Oh, we'll go to kilopascals. Okay? So if we needed to convert 970 millimeters of mercury to kilopascals from prior knowledge, what would we do first? Well, take 970, okay? Actually, that's still a three-step problem. What I meant to do was, how about atmospheres? Would that be, is this going to be easier or harder than kilopascals, do you think? Just flip a coin. It's going to be easier. Why are you right? Yeah, it's 2 steps instead of 3. Okay? So, in order to do this, how many millimeters of mercury are in an atmosphere? So, where would that number 760 go? Up top or down below? It goes on the bottom. You are right. Why are you right? We're canceling that out. We've got 760 millimeters of mercury. Okay. And that many millimeters of mercury equals how many atmospheres? Just one. One atmosphere. So once we divide them two, we have our answer in atmospheres. Okay? Which, what is it, 1.12 or 1.28, all right? Okay, one last thing, like what we talked about yesterday. Let's say we've got this submarine down at 6 atmospheres of pressure, okay? So if we have 6 atmospheres, we want to know, well, how many kilopascals would that be? Okay, so how do we get rid of that atmosphere? So for every atmosphere, how many kilopascals do we get? Yeah, it's up here too. 101.325 kilopascals. Okay? Multiply them two and you got your answer. Left outside, are we good? Okay. Right middle. Okay. Middle. Okay. Right middle. Right. Oh, I meant right outside, sorry. Okay. And left middle. Best ones last, is that right? We just nod our head to say yes, or because we think that's true, or both. It's true. Oh, it's both. All right. So when we get your first paper, which I don't know if we'll have it yet tomorrow, we'll see how that goes. Tomorrow's Friday. Yay, right? And I think probably not, because we're all busy on Monday. Monday after school. Okay? And if I'm not mistaken, okay, I guess we don't need to be having this on the recording. Okay? So we'll catch up to you next time.